Assalamu alaikum dear students. Today we are going to discuss groups of order 30, and we want to see that there are four possible groups of order 30. So let's prove these groups with the help of Sylow's theorem. Uh, Today also we want to see uh, applications of Sylow's theorem to establish all possible groups of order 30. Okay, so let order of G is equal to 30, which is equal to 2 into 3 into 5. Okay, first at all, I will show that a group of order 30 has a normal cyclic subgroup of order 15. Why I am saying cyclic? Because in previous lectures we have established that a group of order 15 is cyclic, right? In fact, we have shown in journal about the order of PQ, and under certain conditions we have established that a group of order PQ where P is greater than Q and P is incongruent to 1 modulo Q is cyclic. So in particular a group of order 15 is cyclic. So my first idea is to show that a group of, in either case, G has a normal subgroup of order 15, of course, and a group of order 15 is cyclic. So G has a normal cyclic subgroup of order 15. So how you can prove? One thing is very much clear that if there is a subgroup H of order 15, then index of H in G would be equal to order of G by order of H, that is 30 by 15, which is 2. And you know that any subgroup of index 2 must be normal in G. So in this case you have H as the normal subgroup of G, and also you know that a group of order 15 is cyclic, so it is a normal cyclic. But we will establish with the help of Sylow's theorem. So let's prove this. Then by Sylow's first theorem, by Sylow's first theorem, G has a Sylow 3 subgroup and G has a Sylow 5 subgroup. Okay, because we want to discuss a normal cyclic subgroup of order 15, that's why I am taking a Sylow subgroup 3, Sylow 3 subgroup, and G has a Sylow 5 subgroup. Also G has a Sylow 2 subgroup as well. But I want to know the number of Sylow 3 subgroup and number of Sylow 5 subgroups. So assume NP is the number of Sylow 3 subgroups, N3, and then N5 is the number of Sylow 5 subgroups in G, where order of G is equal to 30. Let N3 and N5 be the number of Sylow 3 and Sylow 5 subgroups in G. Okay, we assume that NP N3 is the number of 3 Sylow's 3 subgroups, and N5 is the number of Sylow 5 subgroup, and you know that these both numbers are in fact the divisors of 30 and are congruent to 1 modulo 3 and 1 modulo 5 respectively. right? Then so by Sylow's third theorem, N3 is congruent to 1 modulo 3 and N5 is congruent to 1 modulo 5, or N3 is equal to 1 plus 3t and N5 is equal to 1 plus 5t. You can say T dash, where T and T dash belong to Z. Okay, so now from here, by substituting the values of T and T dash, you will get the maximum number, maximum possible number, that is in fact the divisor of 30. Okay, so from here this is very clear. This implies the N3 could be 1 when T is 0, and when T is 1 this is 4, when N T is 2 7, when T is 3 10. Okay, 10, then 4 12 13 is not a divisor, then 15 plus 1 16 is not a divisor, and also 16 is greater than the half of the 30. That's why these are the possible cases. Okay, similarly, and N5 could be 1, and if you put T dash 1, that is 6 is the divisor of 30, 6, and then 3, if you put 3 15 plus 1 16, now 16 is not a divisor of 30. So these are the possible cases. Now we will discuss. Now N3 is equal to 1. Mean if N3 is equal to 1, then the Sylow 3 subgroup, say this is H, is normal in G. Now if N3 is equal to 1, then Sylow 3 subgroup, say H is normal in G. That is, H is normal in G. So if H is normal in G, then you can have a quotient group G by H. This means that G by H is well defined. The structure of quotient group G by H is well defined since H is normal in G. Okay? But then G by H is a quotient group of order G by H, which is equal to order of G by order of H. This is equal to 30 by, what is the order of H? It was a Sylow 3 subgroup. It was a Sylow 3 subgroup. This is equal to 10. And 10 is equal to 2 into 5. So this means that G by H has a normal subgroup of order 5, right? This is a 2p. Its order is 2p. This shows that, this means that G by H has a normal subgroup of normal subgroup N by H, where N must be normal in G and order of N by H must be equal to order of n by order of h. And what is order of n? Here n by h, the order of n by h is equal to okay, since H is normal in G, so this quotient group, the order of this quotient group must be 10, which is equal to 2 into 5. So if you take a subgroup of this group G by H of order 5, then its index must be 2, so that must be normal in G by H. This means that G by H has a normal subgroup n by h, where n must be normal in G, because the index of this subgroup in G by h must be 2, and this is a group of order 5 is n by h, where n by h is equal to 5. Look, because the index of this group in G by h, I mean say the index of n by h in G by h must be equal to order of G by h divided by order of n by h, and this is equal to basically 10, and this is 5, this is equal to 2. Yes, so G by h has a normal subgroup n by h. Of course n must be normal in G, right? So n by h is equal to 5. So from here you can find the order of n. But this implies order of n by order of h must be equal to 5. So this implies order of n is equal to 5 into order of h. And what is order of h? H is a Sylow 3 subgroup of order 3. H is a Sylow 3 subgroup of order 3. So this is equal to 5 into 3, which is equal to 15, right? Hence n is a normal subgroup of G of order 15, and previously in a previous lecture I have shown that a group of order 15 is cyclic. Thus in this case G has a normal cyclic subgroup of order 15, right? Thus in this case in this case G has a normal cyclic subgroup of order 15. As we know that a group of order 15 is cyclic, and this is also normal, as we know a group of order 15 is cyclic. Okay, you can watch this lecture where I have shown that a group of order 15 is cyclic. In fact, under some certain conditions we have generalized the idea of group of order PQ, where P is greater than Q and P is incongruent to 1 modulo P, 1 modulo Q. That's why this is cyclic. Now the second case, that was when NP is equal to N3 is equal to 1. Now if N3 is equal to 10, what will happen? Now if N3 is equal to 10, you know that N3 was remember N3 was 1 plus 3t, so N3 the possible values were 1 and 10. Because 1 and 10 are the only divisors of 30, you know that N3 should divide 30. One thing is, if you substitute the values of t, where t is an integer, you see that when T0, this is 1, when T3, this is 10, and when T4, you are getting 13, not the case. When 5, 15, 16, it is greater than half of the 30, so can never be a divisor. And further, you cannot find any other divisors. So these are the only two possibilities. So we have discussed this case. Now, if n3 is equal to 10, this means that if n, then G has 10 Sylow P subgroups, Sylow 3 subgroups, of order, then G has 10 Sylow 3 subgroups of order 3. And you know that any two Sylow 3 subgroups in G must be conjugate to each other by Sylow's second theorem. That's why they all are intersecting in the identity element, right? But by Sylow's second theorem, these 10 Sylow 3 must be conjugate to each other hence all these must intersect in the identity element. Hence these 10 Sylow, these 10 Sylow 3 subgroups must intersect over the identity only, that is P3I intersection P3J must be equal to E for all I is not equal to J, and I is equal to J is equal to 1, 2, 3 up to 10. So P3, I am labeling the Sylow P Sylow 3 because you have assumed H, so H is one of the P3I, either H is equal to P31 or H is equal to P32 or H is equal to P3. So H is a Sylow 3 subgroup and there are 10 Sylow 3 subgroups, so H is one of these 10, right? Okay, now come to the other case. What will happen with NQ? Now if N5 is equal to 6, right? Okay, from here we can also infer that, you know that a cyclic, a group of order 3 must be cyclic. So these all are in fact groups of order 3. So there are two elements of order 3. So by counting over all these 10 groups, we will get that there are 20 elements of order 3 in G, in fact. Okay. So from here we can also discuss that. But all these 10 Sylow 3 subgroups are cyclic, containing two elements of order 3, thus there must be 2 into 10, that is 20 elements of order 3 in G, and 1 is the identity element, so you have counted 21 element. Now we discuss the second case. If now if Q5 N5, you have labeled N5. Now N5 is equal to 6. I mean to say that if you have number of Sylow 5 subgroups is equal to 6, you know that you have calculated the possibilities that either NQ is equal to 1 or NQ is equal to 6. Now if you have N5 is equal to 6, means you have 6 Sylow 5 subgroup, and you know Sylow 5 subgroup of order 5 must be cyclic also. So there must be 6 into 4, 24 elements of order 5. So thus this case would not be possible, because 24 plus 20, this is 44, and you have just 30 elements in your group G. So that's why this case is not possible. Okay? If n is equal to 6, then a Sylow five subgroup being cyclic, you know, a subgroup of order 5 must be cyclic because 5 is a prime number. Being cyclic, then a Sylow 5 subgroup contains 4 elements of order 5. You know that a cyclic group of order 5 contains 4 elements of order 5. You know that if it is the case, then x5 should be equal to E. So the elements x, x cube, x4. These are the elements of order 5. Because you know that if G is a cyclic group generated by x of order n, then all powers of x which are relatively prime to n also generates G. I have referred this theorem in my last lecture as well, so you can better understand by watching last lecture as well. Okay, so being cyclic contains 4 elements of order 5. Thus, since there are 6 groups of Sylow 5 subgroups, so they contain 24 elements of order 5. Since G has 6 Sylow 5 subgroups, so G must contains 6 into 4, that is 24 elements of order 5. which is a contradiction. As uh, order of G is equal to 30 and G has 1 plus 1 is the identity element, and 24 elements of order 5 and 20 element of order 3, and there may be some more elements of order 2 as well, because G has a Sylow 2 subgroup as well. So that's why plus so on, which is of course greater than 30, right? So this case is not possible. N5 is equal to 6 is not possible, right? Remember this thing. So that's why you have a contradiction, okay? So if you take N5 is equal to 6, then of course G has 5 elements of order. G has 4 elements of order 5, and since there are 6 Sylow 5 subgroups, so that's why 6 into 4, that is 24 elements of order 5. So ultimately the counting of elements is of course greater than 30, which is the order of G. So that's why this case is not possible. Hence N5 must be equal to 1, right? Okay. This means that N5 is equal to 1. This means that K, a Sylow 5 subgroup, is normal in G. Okay. Hence N5 is equal to 1. Thus a Sylow 5 subgroup, say K, is normal in G. That is, G by K is well defined. Okay. By going on similar fashion as we have explained in case 1, that if K is normal in G, then G by K, this quotient group, is possible. Then what is the order of this? And order of G by K is in fact order of G by order of K. This is 30 by 5. You know, K is a Sylow 5 subgroup, and since G has a Sylow 5 subgroup of order 5, that's why it's order 5. So this is equal to 6, which is equal to 2 into 3. Again, look at here. It's 2p. Again, this group has a normal subgroup of order 3. This means that then G by K has a normal subgroup N by K, where N is normal in G with order of N by K is equal to 3. Now I am going on similar fashion. Since G by K, order of G by K, order of G by order of K, this is 6, which is equal to 2 into 3. Again, a group of order 3 must has index 2, so must be normal in this. So G by K has a normal subgroup N by K, where N must be normal in G, with N by K order of is 3. Now again you see this imply order of n by order of k is equal to 3. So this imply order of n is equal to 3 into order of k, which is equal to 3 into 5, which is equal to 15. So this imply order of n is equal to 15. Yes. Again I have shown that there is a normal subgroup of order 15. And you know that any group of order 15 is in fact cyclic. So in this case, you have a cyclic group of order 15 as well. Thus in either case, it is clear that G has a normal cyclic subgroup of order 15, where order of G is equal to 30. Thus in either case, it has been established thus in either case G has a normal cyclic subgroup of order 15. Let n is equal to x, I get x power 15 is equal to e. It's a normal cyclic where n is normal in G, where order of G is 30, and also you have a Sylow 2 subgroup. So you take let M be a Sylow 2 subgroup in 30 as well. Let M be a Sylow 2 subgroup in G as well. Then M must be equal to y, side that y square is equal to e. You know that subgroup of order 2 is cyclic as well. So since 2 is also a prime divisor of 30, so there must be a Sylow 2 subgroup as well. So for sake of convenience, I am taking that M as a Sylow 2 subgroup in G. So M must be equal to of the type y is equal to y square is equal to e. But then yx, y inverse, we are using the previous idea. Since n is normal in G, so yx, y inverse belong to A n, where y belong to M, which is subset of G, so y belong to G, right? If you take x from here, n, then yx, y inverse must be an element of capital N, where you are choosing y from capital N. Of course, y is an element of G as well. And since n is a cyclic group whose generator x, so this must be some power of x. You know that the elements of a cyclic group is in fact the powers of the generator x. So that's why this element must be some power of x. So then yx, y inverse must be equal to some x power r, where r is less than 15. Okay. Now we will find the possibilities over r, and we will show that there are 4 possibilities, and these 4 possibilities are in fact generating 4 possible groups, and these are the those would be the 4 possible groups of order 30. Now work on it as we have done previously in my previous lecture. You take yx, y inverse square. What is the answer of yx, y inverse? Now yx, y inverse square, this is equal to yx, y inverse into yx, y inverse, which is equal to, this is identity, so this is in fact y x square y inverse. Okay, so you take power r on both sides. So this implies yxy inverse power r. If you're taking square, square is shifting here in the central element. So if I'll take r, this would be equal to yx r y inverse. And what is this? Say this is number 1, equation number 1. Putting here the value of x power r, you're getting y, and what is this? This is x power r. So this is yx y inverse, and what is this? From here 1, this is x power r. So you have x power r is equal to y square x y square inverse, and you know y square is equal to identity. So this is equal to e x e inverse, that is equal to x using 1. This is using 1. Okay. So from here you see that and this must be equal to x power r square is equal to x. This implies x power r square minus 1 is equal to e. But order of x is, what is the order of x? X was the generator of Sylow 3 subgroup. X was the generator of Sylow 3 subgroup, right? Sorry, Sylow 15. X was the generator. You have taken n is equal to x, I get x power 15 is equal to e. X was the generator of your normal cyclic group, but order of x is equal to 15. So by 2 and 3, we get 15 divide r square minus 1, right? Okay. Since 15 is the least positive integer for which x power 15 is equal to e, and this is something else, x square r square minus 1 is also providing you identity. So you know that if order of x is defined, then any other power also can generate e if and only if the order is in fact a divisor of that one, or that one is a multiple of the order. So since x power r square minus 1 is the identity and order of x is equal to 15, and 15 is the least positive integer, that's why 15 is dividing r square minus 1. So 15 divided r square minus 1. Now using the congruence relation, you will get so this implies r square is congruence to 1 mod 15. You know that if m divide a minus b, if and only if a is congruence to b mod m, right? So this is the quadratic equation. You can find its solutions manually. One of the simplest idea is you take the remainders of 15, which are 0, 1, 2, 3 up to 14. You put all the values step by step here in R, and those values which are satisfying this congruence are in fact the solutions. So you can do this. For example, if I put 1 square is 1, it is satisfied. If I put the other one is like 3, 4, 4 square is 16, 16 minus 1 is equal to 15. So from here R is congruence to 1, 4, and the inverse of 1 is then 11, then 14. Because if you set here 11 square 121, 121 minus 1, this is 120, and 120 by 15 divided by 15, 5 3s are 15, 5 2 10, 24 3 8. Yes, 11 is working. Similarly, you see 14 square, 196 minus 1, this is 195. So 195 by 15, again 5 3s are 12, 5 3 5 9 and 3 13. Yes, these are the possible solutions. These are the possible solutions. Mod 15. Okay, what is the idea? Whenever you want to solve this quadratic congruence in modulo 15, we have certain formulas, direct formula. If someone of you know number 3, he or she can apply directly. But some of you have no idea about the solution of quadratic congruence. For those, the simplest idea is to put all the remainders in a set. So you know this is 15, you put the remainder 0 to 14 and then substitute here 1 by 1. You will get the answer. So these are the 4 possible solutions of this. And also this can be solved, you can write R square congruence 1 mod 3 and R square congruence 1 mod 5, and then you solve both simultaneously to get the answer, right? I can do that also. If it seems to be difficult to you, from here I can write R square congruence to 1 mod 3 and R square congruence to 1 mod 5. So from here, if you add 3, R is plus minus 1, R is congruence to plus minus 1 mod 3, that is R is congruence to minus 1 will be 2, 1 and 2 modulo 3, and from here R is congruence to plus minus 1 mod 5, right? So R is equal to 1 and 4 mod 5. Now from 1 and 2, 2 is not here, but if you write R is equal to 2 plus 3t and put the values here of t, then t is equal to 0 to t1, because you want to see in modulo 15. Then t2 8, 9 to 11, and value when you put 3 you will get 11. So 11 is here. After that you have to check that whether these are the solutions, so you will find that 11 is the solution. And similarly you can find from here 14. From here, if you multiply 10 plus 4 is 14. So these are the possible solution, or you can find directly whatever you want, because this is a simple question of number theory. You need to know that how you can solve this simple quadratic congruence. Okay, now put 1 by 1 in your case. So if R is equal to 1 mod 15, this implies R is equal to 1 plus 15t. Put in 1 where t belongs to 0. What was your 1? 1 was y inverse was x power r. This was x power 1 plus 15t, which is x power 1 into x power 15 power t. And you know x power 15 is identity power t is identity, this is x. This is equal to x. So this implies yx is equal to xy. Okay, so in this case the group is abelian. For the first case, this is abelian, and also you can have yx power 30 because all are the relatively prime to each other. When all are relatively prime to each other, then you can raise the power. Okay, so now yx power 30 must be equal to y power 30 x power 30, since yx is equal to xy. So you can separate the power like this, and this 30, this is equal to y was the element of order 2. So where 2, 15 and x 15, 2, that is E. So this implies order of yx is equal to 30. So this implies g is equal to yx, sorry that yx power 30 is equal to E, which is in fact isomorphic to C30. Now, if R is equal to 1, then your group of order 30 is in fact C30, right? Now come to the other cases. Okay. If R is congruous to 11 mod 15, 14 mod 15, and 14, you know, you can write 14 as minus 1, which is also congruous to minus 1 mod 15. This modulo can be added and can be subtracted any number of time, any time. So that's why 14 is in fact minus 50, because if you add 15 is minus 1, you are getting 14. So this implies R is equal to minus 1 plus 15t, where t belongs to z. Put in 1. Put in 1 to get y inverse is equal to x power r, this is x power minus 1 plus 15t, which is x power minus 1, x power 15t, which is x power minus 1. So this implies yx is equal to x inverse y. So this implies g is equal to xy, such that x power 15 is equal to 1 is equal to y square, and yx is equal to x inverse y. And you know what is this? This is isomorphic to D15. Some people like to write D15. Dihedral group of order 30. This is D15. This is dihedral group, right? And similarly, if you write the other two cases, you will get other two groups. Similarly, if R is congruous to 4 or 11 mod 15, then G is equal to xy, such that this is actually G2, this is G3. The first one is the cyclic group. G1 was C30, G2 is D15, and what is G3? xy, such that x square is equal to y, x15 is equal to y square is equal to identity R1, whatever you want to write. This is identity, and yx is equal to, you will find here yx is equal to x power 4 y. And the third one is, and G4 becomes xy, such that x power 15 is equal to 1 is equal to y square is equal to 1 or identity, we have no problem, right? And with yx is equal to x11y, right? So these are the possible groups, and after studying direct product and semi-direct product, I will further elaborate that these further can be written in terms of direct product. Of course, these are the groups of order 30. So now, till now, you have established 4 possible groups of order 30. One is C30, other is D15, which is the dihedral group of order 30, which is of course a non-abelian group, and these are the 2 other groups. Because when you put R4 plus 15t, you can absorb, because x power 15 is equal to e. So you will get ultimately y inverse is equal to x power 4 instead of r is equal to 4. So you are getting this, and y inverse can be shifted on the right side to get these two groups. Yes. Finally, you have established 4 possible groups of order 30. So this means that we have classified the groups of order 30. There is one abelian group, which is C30. The order is non-abelian, D15, and rest of the 2 groups. And we will discuss furthermore these 2 groups after studying direct product and semi-direct product. Thank you very much. Allah Hafiz.